Okay, now we're moving on to the perfect square trinomial. I'm just going to abbreviate that as PST. In case I want to come back to it and not spell out the whole thing, I can just write PST and you know what I'm talking about. So I mentioned that there are two different formulas for it, which I put into one formula, but now let me separate it into different ones so you can see what I'm talking about a little bit more clearly perhaps. One is where you have a positive number here, okay, positive term, and that gives you a positive over here in the binomial. The other one is where you have a negative, and that gives you a minus here in the binomial. That is squared. So here's the trinomial, there's the square of the binomial, the perfect square trinomial, so-called. Oftentimes people ask me, where does the 2 come from whenever I'm showing how to solve these things? Well, it's always in the formula. It has to be there, and let me show you why. Let me go ahead and check the positive case, and I leave it to you to check the negative case, but here's where that 2 comes from. Perhaps we can see it when we're multiplying the binomial squared. So let me take a plus b squared. I'm going to multiply that out and see if I get that trinomial. So what this is a plus b times a plus b. Probably one of the most common mistakes I see is for people to try to distribute that square to those two other terms, but you can't do that if there's a plus here. What it's telling you is that you're multiplying this binomial by itself however many times that you have this power here. Now it's only 2, so we're only going to do it twice, but if I had a cube, then you do it again, 4th power, again, so on and so forth. Let me then go ahead and multiply these guys. In the standard fashion, which in general is just everything from one set gets multiplied by everything in the other set. So, how does this come out? A times a squared, plus ab, plus ba, or I could call that ab, plus b squared in the end, which equals a squared plus, notice when I add those two guys up, that's where that 2 comes from, 2ab plus b squared. So this guy is just ever present. It's part of this general formula. So that being said, let me show you how to use this idea here, this map, with several examples. First one being, let's start with one that we could factor in a different way. Well, in fact, you can always factor these in a different way. Any of these trinomials that qualify as a perfect square trinomial, you can factor using methods 1, 2, or 3 that I've shown on previous videos. So let's see what this looks like. I don't have a trinomial yet. Let's make one up. Plus 6x plus 9, let's say. Now, any trinomial may or may not fit this definition of a perfect square trinomial, so there are some things that we need to check. First of all, is the first term something squared? Is the last term something squared? So let's see. Yeah, the first term, I'm going to match it up to my little formula over there and call it a. So a is equal to x, because if I square x, I get that x squared. Looking at the last term, I can say b is equal to 3, because if I square 3, I get 9. Now here's the thing that you absolutely need to check to see if it's a quote-unquote perfect square trinomial, and you're going to do that to see whether or not you can use that formula there. You have to check the middle guy. Is the middle guy equal to 2 times a times b? 2ab, let's check it out. That would be 2 times x times 3, which comes out to 6x. So yeah, it is a perfect square trinomial. That means that I can go immediately to the solution, which is x, I'm going to put a plus because there's a plus here in front of the 6x, 3 squared. And that's it. X squared plus 6x plus 9 equals the quantity x plus 3 squared. Let's take a look at another example and apply the same principles. But let's make it perhaps a little bit more difficult. How about 4x squared minus, here, let's do this one, 28x plus 49. So I'm making the numbers a little bit larger. Whenever I see a lot of numbers, I try to find a greatest common factor. There's a 4, obviously, in this one. There's a 4 in that one, but there is not a 4 in that one. There's a 7 in this one. There's a 7 in that one, but there is not a 7 in that one. So no, there is no greatest common factor. But I'm curious whether or not this is a perfect square trinomial. Why would I even be curious about that? Well, because I noticed something right away. What I noticed was that this thing is a perfect square. 4 is a perfect square. And clearly x squared is also a perfect square. So I can say, if I'm trying to match it up, a is equal to 2x, because 2x squared is 2x times 2x, which gives me 4x squared. And also I noticed right away that the last term, 49, is a perfect square. 7 squared is 49. If the first and the last terms are perfect squares, that's your key to maybe look for a perfect square trinomial. But we got to check this middle term. It's got a minus here, so I'm looking at the minus case. We need to check minus 2ab, or negative 2ab. So negative 2ab, what does that look like? It looks like negative 2 times 2x times 7. And let's see how that comes out. 2 times 2 is 4 times 7 is 28. We have the negative, so yeah, that is negative 28x, which is the middle term. Therefore, this is indeed a perfect square trinomial, which comes out to, parentheses, a minus b, parentheses, squared. So here's my a, 2x minus b, quantity squared. And that's it. If you said 2x minus 7 times 2x minus 7, indeed, that's the same thing. But what if this one were a little bit different? What if it were, for example, 4x squared minus 14x plus 49? Okay. What if it looked like that? Well, obviously, a would be the same as this, 2x. B would be 7, because these are the same, right? But if you tested this, the negative 2ab, from here, you would not get the middle term. So this is not a perfect square trinomial. Now, that doesn't mean it's not factorable per se. With this trinomial in particular, it turns out it is not factorable. So I'm going to call it prime. However, I want to caution you that just because it's not a perfect square trinomial doesn't mean it's not factorable. It just means you got to try something else. You got to try method 1, 2, or 3, or go somewhere else with it. So let me do one more, perhaps. Let me erase this guy over here. And let's just look at one that is not a perfect square trinomial, but that does factor, just to show you that case. So here's a simple one. Suppose I said we started out with x squared plus 10x plus 9. Okay. Now typically, if there is not a coefficient in front of x squared, I don't even mess with this perfect square trinomial stuff, but it does apply. And it's instructive to look at this one just to see what happens if it's not a perfect square trinomial. So suppose we were saying, okay, a is equal to x, b is equal to 3. Those are the two square terms in the front and the back. Now I want to check what is 2ab, and I'm using a positive 2 here because there's a plus here. That would give me 2 times x times 3, which is 6x, which is clearly not equal to 10x. Therefore, this is not a perfect square trinomial, but it doesn't mean that it's not factorable. And in fact, it is factorable. And let me show that. Make some space here. Remember that if that leading coefficient is 1, we can do this in a real snappy way. We can just take a look at the constant term, 9 in this case, and look for two of those factors. 1 times 9, 3 times 3, negative 1 times negative 9, negative 3 times negative 9. Look for the two factors that also add up to this middle term, and in this case, it's 1 and 9. Therefore, this factor is immediately into x plus 1 times x plus 9. So just because it's not a perfect square trinomial doesn't mean that it doesn't factor. It just means you might have to go for something else, some other method. Actually, let me show, I did want to show one more. And I wrote this one down. Here we go. This one is a perfect square trinomial, but here's one of those cases where the numbers are pretty ugly, which is perhaps why you might be motivated to look for a perfect square trinomial. Look how large these numbers are. First thing you do is you look for a greatest common factor. If there isn't one, then okay, that doesn't work, which I don't believe there is. Okay. If you were to try method number 1 to try to factor this trinomial, then you would look at all the factors of 144 and all the factors of 121, and you're trying to come up with the sum of products, the right combination that gives you this middle term. If you're doing method number 2, then you're going to multiply these two guys together, the first and the last. You're going to get a single number and then factor that single number into two things that also add to this middle term. Although, look what you get. If you multiply 144 by 121, that is a huge number with a lot of factors to choose from to try to find the one that sums to negative 264. And that can be a lot of work. So one other thing, you could try method number 3, or, 144. It looks so familiar to me, and so does 121. Both of those are perfect squares. So I'm going to check the perfect square trinomial. So then A would be 12x, because 12x times 12x gives me 144x squared. B would be 11, because 11 squared is 121. So now I need to check what is negative 2ab. And I'm using the minus sign because there's a minus here. And again, that 2 is ever present, comes from the formula. That would give me negative 2 times 12x times 11. And what do we get when we multiply this? Indeed, 2 times 12 times 11 comes out to 264. So this does come out to negative 264x. It checks out. It means that is a perfect square trinomial. And once you determine that, you can go straight to the solution here, which must be 12x minus 11 quantity squared. Again, that minus here is because we have a minus right there. So there's, when you see things like that, perhaps the motivation for checking the perfect square trinomial as opposed to going through method 1, 2, or 3. So let me move on to the sum and difference of cubes, and then I think we'll be done with factoring special forms.